fraction. Yeah.
Whoa.
Okay, so we need to get started then. Been a long time coming. Okay, so we are looking at question, we're just going to start with question 1. We'll make the appropriate skips when necessary. If you have any really in-depth questions, make sure you let me know when we get to your question, to the corresponding problem number, okay? Okay. All right. So we are at number 1. Great. Number 1. Okay, so number 1 we have the integral from 2 to 5, 2 over 3x plus 1. And this looks to me like it's pretty clear-cut that we should be using a U-substitution and not integral by parts. So U, that's going to be equal to 3x plus 1. du is equal to 3dx, which is great because now we know that dx is equal to 1/3 du. So I'm just going to worry about the antiderivative for now. Antiderivative here, this is going to be the antiderivative of, well, the 2 is still there. 3x plus 1 becomes u. Dx becomes 1/3 du. We do some combining, and we find we get 2/3 antiderivative of du over u. Great. That is 2/3 natural log of the absolute value of u plus constant. Of course, that's 2/3 natural log of 3x plus 1 plus constant. Not quite finished yet, though, because this is actually a definite integral problem. So now if we want to go from 2 to 5 of 2 over 3x plus 1 dx, that's going to be equal to the antiderivative 2/3 log 3x plus 1 evaluated from 2 to 5. Substitute 2/3 of log 16 minus 2/3 of log, what is that? 6 plus 1 is 7, right? Log 7. Okay. All right, we can factor out a 2/3 from both. And this is just simplifying now. And using properties of logs, we have 2/3 of the natural log 16 over 7. That's a lot meatier than I expected, that first problem. Okay. Any questions on number 1?
If it was 2/3 natural log of 16 plus natural log of 7, that rule wouldn't apply.
Yeah, that rule would be 2/3 natural log of 16 times 7. And I don't know what 16 times 7 is, like 1017, 118, 112. I don't know, whatever that is. Okay. Question 2. Question 2, we have the antiderivative of 2x over the square root of x squared plus 1 dx. Hopefully you're kind of getting the picture that most of the time when you see a quotient, your u is going to be some part of the denominator, usually not the power, but the part that's receiving the power. And most of the time when you see a quotient, you're not using an integral by parts. So let's get our U-substitution taken care of. U should be x squared plus 1. Another good way to look at it is the derivative of x squared plus 1 appears right here. That's the derivative. So your u is appropriate. So that's 2x dx. Imagine that. You don't have to solve for anything. You have a 2x and a dx already. You got 2x dx. Why didn't that go yellow? 2x dx, 2x dx. So we're all good with a du. Okay, antiderivative of, okay, all of that turns into a du. All the underlined yellow turns into du. This is now the square root of u, which is u to the negative 1/2 du, which integrates to 2 u to the 1/2 plus constant. Great. That's 2 square root of x squared plus 1 plus that constant of integration again. That's more like it. Nice, easy problem for number 2. Any questions on those 2? All right, number 3. All right, so we've arrived at what looks to me initially to be integral by parts. It's a quotient. One part's algebraic, so that goes to 0. The other part's trigonometric, so that just kind of flip-flops. So this looks to me like a good candidate for the tabular method, right? Tabular method will take care of this really quickly. U is x, dv is cosine 2x. Derivative is 1. The derivative, or the antiderivative of cosine is sine. We have 2x, so that's 1/2 sine 2x. Derivative is 0. Integral is another 1/2, but this time cosine. If you put everything together, you're going to get 1/2 x sine 2x minus negative 1/4 cosine 2x. Looks like I can factor out a 4. Does the answer have it factored out? No, it doesn't. Okay, so that's fine. 1/2 x sine 2x plus 1/4 cosine 2x. Would you believe it? I forgot the c. It's probably the best case scenario for a integral by parts problem, right?
If you did integral by parts, would you still get the same answer instead of the?
Yes.
Okay, so
Yes.
it doesn't matter.
If you did the regular integral by parts method, you'll come up with the exact same thing. It doesn't matter which one you use.
So if we see a problem that we could do with integral by parts, it wouldn't matter which method we use, either
Well,
tabular.
let me be clear about that. You can't really use a tabular method for every integral by parts. Okay, only for some of them. If you decide to use a tabular method, then you will get the same answer as integral by parts.
So is it safer to just use integral by parts?
I would encourage you to use tabular when possible because it is a significant time saver, like significant. Of course, if you're not comfortable with it, don't. Okay, we are on 4. Everyone's favorite. I mean, this is a favorite. This is greatest hits right here. It's good material. Integral by parts again. U dv. I'm going to use the tabular method again because I noticed that my algebraic bit x squared, eventually that's going to turn into 0. And I can take antiderivatives of e to the 3x like infinitely, or as much as I ever will need to. So let's keep going. 2x, 1/3 e to the 3x, 2, 1/9 e to the 3x, and then 0, 1/27 e to the 3x. Positive. So what is that? 1/3 x squared e to the 3x. Next one. Negative. Minus 2/9 x e to the 3x. Positive. Plus 2/27 e to the 3x plus constant. That's perfect. Okay, let's take a look at our denominator. It looks like the least common multiple is 27. So I'm going to factor out a 27 on the denominator. And an e to the 3x. Good. Okay, 1/3 divided by 1/27 is 1/3 times 27, which is 9. 2/9 divided by 1/27 is 2/9 times 27, which is 2/1 times 3, which is 6. This one's easy, it's 2. Just a really quick check. Can I factor the quadratic here? I don't know. 18. Is there a way to get 18 from 6? I don't think so, right? I think this is unfactorable. How about here's one. How about what is the name of that? Determinant. No. What do you call that? Discriminant. B squared minus 4ac. 36 squared minus 4 times 9 times 2. Oh, that's definitely negative. The discriminant's definitely negative, so you can't factor this, right? Okay, so that should be the answer. Actually, I just have the answers in front of me, so I can take a look. Oh, yeah. Why did I just factor out a 3? Lame. Gotta fix that. I just factored out x over 3. Lame. Next year they'll have it better. Okay, any questions on 4? Hmm? Yeah, you could have factored out a 1/3, but you know, I think that the whole idea of factoring is to make something look simpler. That usually means, you know, less fractions, really. Yeah, I know. I mean, we're kind of at that math place now where you know what equivalent answers look like and what aren't equivalent answers. Okay. Let's take a look at 5 then. We get
the other one's on its way. What looks like what you do.
What do you mean the other one's on its way?
We ordered them at separate times, and the guy he's gonna call the guy who's on his way here back so he can clean the bunch on.
Horrible. Okay. Integral by parts or U-substitution. That's pretty much what we need to do. Can we use a U-substitution? That's really the question. Can you use a U-substitution? Yeah. You notice that inside the square root is a second degree. Outside of the square root is first degree. So the degree decreases, meaning there's a derivative involved here somewhere. So u, we're going to call u 4 minus 9 squared. Darn it. We're going to say u is 4 minus 9x squared. Make sure you don't set the power, in this case the 1/2 power. Make sure you don't put the 1/2 power as part of u. Du is negative 18x dx. That's just our derivative again. We'll do our matching game. We have an x dx, x dx. Looks like I have to get rid of that negative 18. So that tells me negative 1/18 du is equal to x dx. Sorry. That's equal to antiderivative of. Okay, all of that underlined yellow stuff turns into 1/18 du. So just the square root of u, negative 1/18 du. That's negative 1/18 antiderivative of u to the 1/2 du. So that's equal to negative 1/18. 1/2 plus 1 is 3/2. So 2/3 u to the 3/2 plus constant. Simplify that one last time. That's negative 1 over 27 square root of 4 minus 9x squared cubed plus constant. I see the solution manual has it at the 3/2 power. What do you do? It's not that bad. Should we get 6? 6. Okay. Again, your choices are integral by parts or U-substitution. Always give priority to U-substitution. It's easier, it's faster. Inside the square root is definitely 1 degree more than outside the square root. So I would encourage you to use a U-substitution here. U equals x squared plus 1. du equals 2x dx. There's my dx. There's my x. I don't have a 2. So let's divide that over. 1/2 du is equal to x dx. That's going to be a nice clean substitution. Okay, so let's forget about the integral, or definite integral for a while, and let's just work on the antiderivative. This turns into the antiderivative of u to the 1/2 times 1/2 du. Which is 1/2, 2/3, u to the 3/2. Which is 1/3 square root of x squared plus 1 cubed from 0 to 1. Okay, let's do our substitutions. 1/3 square root of 2 cubed minus 1/3 square root of 1 cubed. Okay, it looks like the solution manual has a 1/3 factored out. Let's factor out a 1/3. We'll get the square root of 2 cubed minus 1. Or I don't know if you'd prefer to see it this way. That's 1/3 of 2 root 2 minus 1. Alternatively, you could also do 2 root 2 minus 1 over 3. That's an answer too. All perfectly good. Which one's better? I don't know. As long as you make me divide by 3 only once.
The part where it says 1/3 and the cube root x squared plus 1 cube and then 1 to 0.
Mhm.
Why don't we just change it to the 2 to 1?
You could.
Okay.
You could. A lot of people don't feel comfortable doing that. But you know, if I had my way, everyone would do it that way. Any questions? Further questions on this one, number 6? It's not bad, right? Somehow I feel like this is the way that it should look. Like that. That feels like a book answer, doesn't it? It's like an art. How do I make my answer look like the book's answer? Okay, so find an expression in A and B for the value of the definite integral. Ugh. Okay, well, might as well do it. Antiderivative from A to B, 5x squared plus root x minus 7 dx. Can we talk about the antiderivative first? Hey, what's the antiderivative of 5x squared? Actually, you know what? Let's do it like this. It's the antiderivative from A to B. Sorry, not A to B. Let's not worry about A to B. Antiderivative of 5x squared dx plus antiderivative of root x minus 7 dx. One of those is easier. Actually, they're both pretty easy if you're really comfortable with this by now. But we're going to take the second one a little bit slower. That first one, 5x squared, that antiderivative is 5/3 x cubed. Totally easy. The second one, you're going to have to use a U-substitution. du is equal to dx. That means the antiderivative of u to the 1/2 power. Dx is du. And once you substitute, I think you get your antiderivative. 5/3 x cubed plus 2/3. 2/3 u to the 3/2. Five thirds x cubed plus 2/3 square root of x minus 7 cubed. Yeah.
There would be not U plus C because you're substituting A and B.
Yeah, but right now we're working on antiderivatives. So we're going to do that right now.
For solving when you have parameters on an integral,
Mhm.
could you like rewrite the equation with not writing the parameter, so then you have a plus c, and then kind of just make it reappear with the line?
Yeah, that's exactly what we're going to do right now.
Okay.
We didn't let you do that?
No, because it's like, where did it go? Wrong. Okay.
We're doing the antiderivative first. I think it's all kind of in the way that you write it. Okay. If you make it clear that you're figuring out the antiderivative first, then you know it's fine.
Okay.
But kind of note this: I'm going to actually rewrite the entire thing. That's now going to be equal to 5/3 x cubed plus 2/3 x minus 7 cubed from A to B.
Could we make the radical like S3 halves?
Let me look at the answer. It looks like the answer he does. So, you know, yeah, sure.
Okay, as long as we're not doing something here.
Let's substitute things in here. That's 5/3 b cubed plus 2/3 square root of b minus 7 cubed minus 5/3 a cubed minus 2/3 root a minus 7 cubed. Go ahead and group things together. We got 5/3 of b cubed minus a cubed plus 2/3 of b minus 7 cubed minus a minus 7 cubed. So that looks pretty good. Oh, looks like the answer here didn't factor out the 2/3. So what do you do? What is that, number 7, right? I want to give you guys a break soon, but like the pizza is not here right now. Okay, so let's finish this last one, and we'll get some pizza. Okay, pizza time. That's good. I'm gonna leave this on, and like you should like periodically come to the camera and like with a piece of pizza and just like eat it. Okay, last one before our break. We got a doozy actually. We've got number 8. We've got e to the 4x y prime. That does not look like a 4x. Y prime equals x. That's great. We're supposed to solve the differential equation. I think this is the 3rd one we've done. So first thing, that y prime is useless in a differential equation. Totally useless. E to the 4x dy dx equals x. Okay, we want to move all the x bits to the right, all the y bits to the left. So it looks like we're going to divide by e to the 4x and multiply by dx, where dy equals x over e to the 4x dx. And that makes the integral look really much more difficult than it really is. Because all you need to do is use a negative exponent, and all of a sudden it becomes super easy. We know how to integrate that. Okay. Can't use U-Substitution, so integral by parts, but it's an easy integral by parts. By easy, I mean this. Pizza 2. Derivative of x is 1. Integral of e to the negative 4x is negative 1/4 e to the negative 4x. The derivative of 1 is 0. Antiderivative is 1 e to the negative 4x. Okay, so what do we get on the left side? We get a y. On the right side, we have negative 1/4 x e to the negative 4x minus 1/16 e to the negative 4x plus constant. I think I can factor out, let's factor out a negative to start off with. Least common multiple of the denominators are 16. Every factor has an e to the negative 4x. Y equals, keep that negative out there. X plus 1 is on the numerator. The denominator is 16 e to the positive 4x plus a constant. Oh, shoot, you're right. I forgot the 4. That's a 4x. Thank you. Okay. Yeah.
Can we put the 4x plus 1 in parentheses? Because the negative is.
You don't have to if the negative is clearly on the side of the.
Justin Abril, please come down to the dean's office. Justin Abril, even if it doesn't sound like your last name, if your name is Justin and you're on the campus, please come down to the dean's office. We have someone waiting for you.
Pizza time?
So they cut one of the pizzas wrong and they cut it into 8 and then the other one they cut it into 12. So, yeah.
Yeah.
For general power rule, that just means integrate, like that's not.
Basically, that's how it is.
Just making that 1 plus 1. Okay, so thank you.
Got paper towels.
It's literally your shop.
I know.
Don't let me touch it.
Anyone want the chips?
$2 for big. Paper small. I don't have a lot of time, but I mean,
That's like two.
I'm just kidding.
I don't know how much to charge. I don't know how, I've never. That's better.
I know it is, right?
Oh, I think.
I get that.
This is the first set. Okay. I haven't watched it.
I have radio. 25. Yeah. I'm just using. Oh, I must
know my mom talked
Wait, is everyone good on pizza? No one wants.
Right.
You don't mind?
I feel like if I had less players, I had more for it. Like, oh,
I just, yeah.
You could have stolen that now.
there's enough for that.
Yeah. Wait, everyone.
Bro, show the sticky dip, show the, you ready for massage? What? English 101, 2, 3. Oh, massage. Yeah. I thought you said massaging. 101. Maybe massaging. Shoja, can you keep your phone on you? Because I'm gonna text you asking me. I gotta go.
Yeah.
Oh my God, why is she? Would you go to college for what?
I had no idea. It looks like it looks.
Three got one.
I think we should
Search the applicant nicely.
Yes, I was even reading. You just come from behind the table, you just sprint. It was like 4 bites. Well, you know, bites. Yeah. It's back when you're in Oh, probably.